Well, I think we can start. Welcome back, everyone. So we're now on week number 12. We're at the 75% mark once this week is completed. But the big announcement for the day is that our third exam will be a week away from today, Thursday, April 14th. The coverage for the third exam is going to be these particular sections. That means the work we're doing on this week is not going to be included on exam 3, since this will give you time to study for these particular sections. Section 3.6 is the one on exponential growth, exponential decay. 3.7 is the one where we're differentiating logarithms. And you can see the formula sheet that's going to be on the last page of the real exam. This will include properties of logarithms. 4.1, we're looking into local minimums, local maximum values, critical numbers, as well as the closed interval method. And then 4.2, 4.4 are pretty similar sections. 4.2 looks into the first derivative test for local minimums, local maximums, the second derivative test for concavity, second derivative test for local minimums, local maximums. And then 4.4, same kind of problems, except they have context. This time there's exactly one critical number, and we're using either the first derivative test to find the absolute maximum or absolute minimum, or we're using the second derivative test to find the same, an absolute maximum, absolute minimum. So just like on the other exams, here are the related to sample versions of problems. These will be a nice rounded off set for a good indication of what can be on the real exam. Version 1 is problems right out of the textbook. And version 2 is just our lecture notes converted into bona fide worksheets to convey the problems that we were doing in class are meant to be highly similar to real exam questions as well. Well, it's pretty much the same rodeo that we've done already for exam 1, exam 2. We're just doing it all over again for exam 3. Great ways to prepare is be fully caught up on these sections in WebAssign, be fully caught up to quiz number 9. Quiz number 9 is relative to section 4.4. Then once you're fully caught up, start working through the sample exam questions down here, and that'll be a great way to round out and give you a great indication of what to be prepared for on the real exam. But any questions or comments whatsoever, folks, about our upcoming exam? Okay, well, when we come back to class next time, to keep caught up in the schedule, we have to continue work through section 4.6, work through section 5.1. But if students have any questions whatsoever about exam 3 material, I'll be happy to help out. So don't hesitate to ask. I'll always call for questions to start off class. And even if you have a lot of questions, it's understandable, another exam is coming up, don't hesitate to throw them out there. I'll be happy to help out. If you're in the online section, check out the inbox system in Canvas. I sent out the instructions on Monday morning for scheduling your exam, which also bounces an email to your ISU email address. And if you're in the in-person section, we'll have our exam on Tuesday in class during the class time. That means next week on Tuesday, we won't actually have class on the 14th. I'll be doing the exam in class. And so that's the ideal time to schedule your exam. And we'll have exams, or excuse me, we'll return to class for on Thursday the 16th. Naomi says, how do we find the absolute minimum or maximum again for exam 3? As far as the absolute minimum or maximum goes, we'd be using these tools here. Actually, I think it's probably easier to open up the formula sheet. Let me open that one up. So you're going to have this provided on the real exam. And when it comes up to finding the absolute maximum or absolute minimum, really there's two good answers to that question. One problem might ask you to use the closed interval method, and the wording would say that directly in the problem. This is a method that we did in section 4.1. It leads to a process of you find the critical number, then evaluate the function at the endpoints, at A, at B, and then also at the critical numbers that you found. Largest value is the absolute maximum. The smallest value would be the absolute minimum. And that's one way to get an absolute max, absolute minimum. But there's more going on with that question that was asked. To get an absolute maximum, absolute minimum, we could also be using either the first derivative test or the second derivative test. As far as the first derivative test goes, there's going to be just one critical number, As far as the second derivative test goes, there will also just be one critical number, and we have to also explain why the second derivative is always positive. Other questions at the moment about maximums, minimums? Okay, well, another way to address that question is quiz number 9 is kind of asking for the same information. Let's open the PDF version of this one. This one is about the size of a predator population P modeled by X, the prey density. So the population of the predator size depends on this function here, where X is the size of the prey density in that region. Here, we're trying to find the maximum predator population size, but this problem is asking you to just use the first derivative test to find that maximum. You could use a second derivative test, but it turns out to be a good amount of work on this one. So finding the first derivative, using the first derivative test on this one to find an absolute maximum means there'll be exactly one critical number in this problem. Pretty much, again, it goes back to the problems that we did in section 4.4. We were finding absolute maximums, absolute minimums in each one of those problems, as well as all the way back to 4.1, where you're using the closed interval method, the last question that we did on those notes for the absolute max, absolute min. Well, any other questions at the moment, folks, before we jump back to section 4.6? Okay, well, here's where we left off on Thursday of last week. We finished off the optimization section, then we only just really scratched the surface of section 4.6. We looked into the initial definition of what we even mean when we say antiderivative. In a certain sense, we're moving backwards, but we have to say exactly what we mean by that. So we say a function, capital F, is an antiderivative of a function, lowercase f, if the derivative of the capital F function equals lowercase f. So an antiderivative solves a property that if you differentiate the antiderivative of the function, you get back the original function. The most general form of the antiderivative adds on an arbitrary constant of integration. And this was our first problem that we got through on example 2. Really, the whole purpose of example 2 part A was just to give us a rule. We have a nice formula coming all the way back from section 3.3, differentiation properties. They gave us the power rule. So this was way back, section 3.3. So it told us if we have x raised to a power, say x cubed, the derivative would be this, 3x squared. The power n comes down, it multiplies, and the new power is 1 less. But if we're using this rule in reverse, because we're looking for an antiderivative, we do everything completely backwards. And even the sequence of steps are completely backwards as well. Instead of the very first thing being the exponent coming down and multiplying, the very first thing we do is we increase the size of the exponent. So we have +1 here rather than a -1. So we go up in the size of exponent. That's the first thing we do. After we have the new exponent, we divide by that new exponent as opposed to multiply. And then, because we're finding the most general antiderivative, we throw in the arbitrary constant c. So this is really our first big formula as far as antiderivatives go. But the good news about antiderivatives is this part right here is essentially just the check. Any formula or any problem you solve, you can find out really fast using methods in 3.3, 3.4, 3.5, and so on, just by differentiating your answer. So when we went to differentiate this, what happened was n+1 copied down. The old exponent, n+1, moved down, and it ended up here. Sorry, that was the eraser tool. Then the new exponent is 1 less. We're just using the power rule. We have a cancellation going this way. And we get the original function, x power n, the one that was right here. So our goal in these notes is really just to practice the process of finding the antiderivative for various different scenarios. And here's our next one we're going to give a try. Y equals 1 over x cubed. Well, any questions at all, folks, with the recap before we try out the next problem? Okay, well, let's imagine we're finding the antiderivative of this thing. Even if you were going to differentiate it, there's one nice algebraic step that's a good idea to take right away. Just rewrite the function in a form that's convenient to work with. The base in the denominator is not easy to deal with. If you were differentiating that, you might reach for the quotient rule, which is like 6 times the number of steps you really needed to take. So rewrite this as x power -3, and whether you're finding a derivative or an antiderivative, this format is way easier to work with. We want the antiderivative of this function, so in the definition above, x power -3 is the function in green. Antiderivative, the function in blue, uppercase f of x, will go like this then. First thing I would write down is the base x, but give it a little bit of extra space after the equality symbol. Then the power rule going in reverse for the antiderivative says you go up 1. You only go down 1 over here if you're taking the derivative, so now the directionality matters. So if it's power -3, going up 1 means the new power is -2. Then we move over to this portion. Once we have that new exponent, we divide by it right away. So this becomes 1 over -2, or we could just rewrite it in a more compact form, -1/2 times x power -2. We have to add on the arbitrary constant c, so we go plus c. And the claim is that's the antiderivative of the function here in green. Well, that's one down. We have many more to go in the notes. After we have the antiderivative down on paper, because the check is so fast, I encourage you to always do it, either in the margin to the right, like we'll do on these notes, or maybe doing it mentally. If you have really good ability to visualize a mental blackboard, do it in your mind, show what this derivative will look like, verify you get back to x power -3. It's not required for full credits, so if you don't do the step on a quiz or an exam, I won't dock you points. But the check is so immediate, we might as well check it out. So here's the check. Whatever you said f of x is, differentiate it. So that's this stage up here on the top where the definition is. When you differentiate this function, we use the constant multiple rule, so -1/2 stays right where it is. Here, we're using the power rule, the ordinary power rule, not in reverse, the normal direction. -2 comes down as an exponent. Then we update that exponent by going down. So think differentiation down, D for differentiation and down. Anti-differentiation, you're going up. So if it was power -2, now it's power -3, one less. This is an arbitrary constant. We're looking for the most general antiderivative, and they all differ by adding any constant whatsoever, whether it's 5, 10, or pi. We write it in its arbitrary form c. It's any real number, but it's a constant, so it just immediately goes to 0. And usually we won't even write down that step in our check. We'll just know, differentiate that constant, wipes it out. Back over here, it simplifies just a little bit. We get that f prime of x. Let me hide that part first. F prime of x is now equal to x powered -3, when the -1/2 cancels with -2. But x powered -3 is the original function, so our work is complete. We can now be extra confident we have the right antiderivative. Again, the check is fast, and it's easy to get mixed up on the direction. Now we're going up on exponents, so if I accidentally put down the wrong exponent here, you'll know that right away, the moment you differentiate it, that it's not going to come out as x powered -3, unless you had specifically a power -2 here. So the good news about antiderivatives are it's just more practice differentiation, really. We're asking one function, can you differentiate to get this original one back, or in its simplified form? So we put down something using a formula, but immediately differentiate it to make sure it's the right thing. Well, that's our first bona fide problem of the day. Any questions at all, folks, getting through this one? Okay, and I recall last Thursday, we made a pretty big deal out of the next one. This one's a little bit different. If you try to put it in the same kind of form like we did here, things will go awry. So let's write this down briefly, but with a warning that this is a miscalculation. So maybe don't copy these steps unless you want to have this as a warning in your notes. If you do copy the steps down, maybe put something like warning, just as a reminder that this is not the right way to do this one. If we were thinking in terms of what we did on part B and they took the same steps, we would write this as y equals x powered -1. And so far, so good. There's nothing really inherently wrong about that step. But then if we go to apply this step here, we would say f of x equals, first thing we did was write down the base x. So here it is. Then we wrote down the new exponent. We have to go up though. It's +1, it indicates in the formula, right? But when you go up 1 on this one, you'll get 0. Then you have to take this step. The formula is now saying you have to divide by 0, but that means this whole thing is undefined. In other words, the power rule in reverse completely and utterly fails the moment the exponent n comes out as a -1, and that's where it is right here, a -1. Power rule in reverse does not work on this one and only one power function. It's a complete breakdown. Really pretty weird, but despite that, it has an antiderivative. Every continuous function has one. This function becomes continuous at the moment we insist the domain excludes 0. So there's an antiderivative to that somewhat, somewhere, somehow. And for this particular function, 1 over x, we actually just leave it in that form. Now, thinking back in terms of what we did in the past, anyone happen to know what the antiderivative might be? One hint is, recall way back, actually not that long ago, but it might feel a while ago, in section 3.7, we had this formula. If you differentiate the natural logarithm of x, you in fact get a 1 over x out, same as that function right there. That tells us we have an actual antiderivative. Yeah, good call, Haley. It turns out natural log x does the job. Derivative of natural log x is 1 over x. That means the antiderivative should just be natural log x plus a constant. But then it gets weirder still. If we want to write the most general antiderivative possible, we want its domain to be as big as possible as well. And this will affect our work way back in chapter 5, or way forward in chapter 5, really just the next section. So whenever this antiderivative comes up, we actually use a slightly different formula. At the very, very bottom of these notes, we had this formula too. It turns out also the derivative of the natural logarithm of the absolute value of x, also 1 over x. And we took a little extra time to derive how that formula goes by differentiation. So this formula becomes relevant with integration, and that's the whole purpose of section 4.6. We need an antiderivative to become fluent with finding definite integrals later on. So when this function comes up, we apply this formula here. Let's write it down in the notes for a good reference. The derivative with respect to x of the natural log of the absolute value of x is 1 over x. We use this function because its domain is bigger than just ordinary natural log x. That domain includes all real numbers except 0, thanks to the absolute value. So here is our next pretty big formula in its own right. F of x is natural log absolute value of x plus a constant c. So we had one formula here, power rule in reverse. And here's our next big formula. Antiderivative of 1 over x. So these are really the two big formulas so far in the notes. Definitely we'll use the power rule in reverse a whole lot. So that formula is going to become second nature in much the same way the power rule has become second nature. But this one's kind of a bigger deal because it feels random, but it will come up in these notes. We'll refresh it when we're in chapter 5. So we'll make a lot of good use of this formula here. And the check is basically what we see on the right. That's the check here in black. Derivative of natural log absolute value of x is 1 over x, and that constant goes to 0 upon differentiation. So watch out for these problems. If it's 1 over x cubed, that's the right strategy to take. But whenever 1 over x comes up, it becomes this most random antiderivative ever. It's natural log absolute value x at a constant. Well, any questions at all, folks, with the part C? Okay, well, I think these are the trickier parts of the notes so far. Deriving the power rule, showing its exceptional case. This is when n is -1. The rest of the problems are going to be pretty standard. And as far as the red goes for my lettering, I changed the order of these problems. And I forgot to actually update the alphabet order. So that's why these are in red after I fixed these after publishing the notes. Well, we need a new antiderivative for the next case, part D. If f of x is e to the x, anyone see what the antiderivative, uppercase f of x, should be? Yeah, good call. The antiderivative of this, just as said in class, is automatically e to the x. A good call, add the arbitrary constant c to make it the most generic antiderivative possible. Why does this one work? Well, it's because if you differentiate e to the x, you get e to the x back. So again, that's still a pretty weird function. Haley says, wouldn't it just be, yeah, absolutely. Just an e to the x plus c, absolutely. So once we have this, again, we can check it pretty quick. The check is take f prime of x, the function that we came up with, but derivative of e to the x is just itself. The derivative of the constant c goes to 0, so we're done differentiating. We're left with e to the x, which is equal to the original function, f of x. And so our work is completely done on that one. So again, e to the x is a strange function. It doesn't matter how many times you differentiate it. It doesn't matter how many times you take an antiderivative of it. You just keep on getting e to the x. Well, let's try out this one. If we can find an antiderivative for a base e exponential, we should be able to do the same for any exponential, right? So here's base 7 power x. Here's where the formulas get a little bit tricky. If we put down on paper some review formulas that we saw in the past, it helps out quite a lot. So even though this is section 3.7 on logarithms, we also reviewed how the exponential functions work at the same time. So if we take the derivative with respect to x of b to the power of x, we get b to the power of x times the natural logarithm of b. So in other words, if you differentiate 7 power of x, that's a coincidence those turned out to be the same. Derivative of 7 power x is just 7 power of x times the natural logarithm of 7. So let's put down on paper this formula to help us out getting the antiderivative. Let's write derivative with respect to x of b power of x is b to the power of x times the natural log of b. With that equation down here, we can get a pretty fast antiderivative. Let's write it out as a formula. So here's our third really useful formula. If f of x is a base b exponential function, b could be e, but it could be 7 or 12 or 1.2, any random base. So if f of x is equal to b to the x, then f of x equals b to the power of x times divide by the natural log of b plus a constant is the antiderivative of f. So that's our next big formula in this box here. Let's think about how it goes, though. In a certain sense, the logic of how we put this antiderivative formula down on paper matches how we derived the reversal of the power rule. If the derivative of b to the x multiplies by the natural log of b, well, then the antiderivative should divide by the natural log of b. So that's why we're dividing there. And then we just tack on the arbitrary constant of integration, that plus c portion. Naomi says, will these formulas as such as the one that you just wrote down be available to us on the fourth exam? Yeah, I'm going to provide some of these formulas on the fourth exam, which would be the final exam at that point. So once we're getting closer and closer to the exam number 4, we'll have the same kind of setup as we saw here. I'll say what the final exam formula sheet is going to be. It'll be a little bit longer because it's a comprehensive exam. And these brand new formulas that we're taking a look into will be part of the help on that as well. Other questions at the moment? Okay, well, we haven't solved the problem yet, right? We just wrote down the formula. So here's our base 7 exponential. The claim is then that the antiderivative f of x should just be 7 to the power of x divided by the natural log of 7 plus a constant. But we need to check that out. So even though we have a formula down, it's really good practice, especially when you're doing this for the very first time, to double check by differentiation. So let's see if this really works out. I'm putting the check in orange just to convey it's not a required part of the problem. The problem's totally solved right here. So if we go and take f of x, differentiate it, let's write this down carefully because you know it's kind of a slightly tricky derivative, mainly because of where we typically put natural log 7 in this formula. But we could rewrite this. An easier way to differentiate this formula is to take the constant, 1 over natural log of 7, and separate it out. This thing where the red dot is really just 1 over natural log 7 times 7 power of x plus a constant. Again, this is the formula that's typically written down for the antiderivative. If you're checking it, this is the format that's easier to check. The reason this is easier to check on a derivative is when you move out this fraction right here, it's just more clear that this is a constant. This is like differentiating, say, 10 times 7 power of x or 10 times x to the power 7. If this is a constant, we're using the constant multiple rule. And so when we go to differentiate, this whole part right here is unchanging. It stays as a 1 over natural log of 7. Then we move over to this part in the constant multiple rule, differentiate the 7 power of x. That means we're following this process. We put a 7 here times natural log 7. So the derivative of 7 power of x is itself 7 to the power of x, multiplied by the natural log of 7, and the derivative of the constant goes to 0. But now, once we have this format, we get a quick cancellation. Natural log 7 cancels from numerator into that denominator of the fraction. You get just 7 power of x, which is lowercase f of x, and that completes the check. So the major idea is, if that's your differentiation formula, but you're going backwards finding an antiderivative, Just take the constant, chuck it down into the denominator, and that's the brand new formula. And this is just the check to show how it works. Well, any last questions or thoughts, folks, on getting through this one? Okay. Well, the roundup of formulas are, we have this really key formula. This one gets used a lot. Power rule in reverse, just much like the power rule gets used a lot. This one, we use a heavy amount for antiderivatives. Then there's the exceptional formula, 1 over x. We have to recall that's a natural logarithm. And maybe let's add just a little bit more emphasis. Absolute value is required for that total formula. If you forgot it and had just natural log x, you get most of the credit. You might lose just a simple point. But for the full correct formula, it has to have the absolute value bars written around it. And the next big formula is this one right here. It actually works in part D, but we know the derivative of e to the x itself, so we usually wouldn't cite this formula. But it's majorly important if we're doing something like in part E. Well, we got through it, folks. Example 2 was really just kind of a roundup of interesting formulas and short problems to find antiderivatives on. Example 3 are like the slightly longer questions, like you'll see in WebAssign, where there's multiple steps to get through the problem to find the total antiderivative. Well, let's get started. Here's our third example. For trying to find the antiderivative, one thought is we would probably take the same exact steps we're about to take if we were going to differentiate this. We don't want to use the quotient rule. Reversing the quotient rule is not something that's typically done. We can reverse a product rule, but that's called integration by parts, and it becomes a very messy procedure. If something is a quotient and we want to reverse it, either rewrite this as a product and use integration by parts, or the better method is just simplify that thing down algebraically. If you simplify that just right, there's no fancy tricks here. We don't need integration by parts. We don't need to rewrite this as a product where it's a quotient, really. And it expands in this kind of way. Even if we were differentiating this function, this would probably be the optimal approach to take. Because hitting this with quotient rule, it's a lot of steps. It'd be a product rule because of the numerator mixed with the quotient rule. But you get out of the product rule as soon as you distribute through in the numerator. You get out of the quotient rule as soon as you divide by x. So the first step is just algebra. We take f of x, distribute in the numerator, completely expanding with the FOIL method to get 3x squared minus x plus 15x minus 5. Divide by x, then simplify the numerator to get 3x squared plus 14x minus 5. All divide by x. So now if you were differentiating this, it's still a lot of work. It's still a quotient rule in that format, but you can sneak out of the quotient rule even if you're differentiating. We're not differentiating, we're finding the antiderivative, but the thoughts and the logic of what we're doing algebraically is one and the same. We want to do this as painlessly as possible, so we divide x into all of the terms. We'll get 3x squared over x plus 14x over x minus 5 over x. So now in our next line, f of x, after simplifying, use exponent laws to get 3x on this term, plus 14 on the second term, and this is the dangerous one. X is in the denominator to power 1. That means the antiderivative is non-standard. A logarithm with an absolute value is going to pop out. So the best way to handle that last term is rewrite it as -5 times 1 over x. Because that exhibits a natural log is going to occur when we find the antiderivative on that part right there. So again, whether you're taking the derivative or the antiderivative, the steps on this one would be about the same. This is doing it as painlessly as possible. Take a couple steps with algebra, and now antiderivative will be taken term by term by term. Okay, so we're ready for uppercase f of x. We want the antiderivative of the function in green, so it's going to turn into this. Let's go carefully using the rules that we know from above. Starting with that one, the way we would write this down is start with the constant multiple rule. Whether you're differentiating or coming up with an antiderivative, a constant being multiplied is not affected. So 3 just copies down, but before you copy down x, give it a good amount of space. Here's that good amount of space. Now where the red dot is, the exponent is actually a 1. We need to go up by 1. So the new exponent is 2. And the moment we have that new exponent, we divide by it. Dividing by 2 means we're multiplying by 1/2. And so you know if you didn't actually give it a lot of space, if you just went 3x squared, you'd have just divided the 3 by 2. That would have been appropriate as well. So that's our first term. And if there's 3 different terms you're finding an antiderivative for, it's not a bad idea to just check as you go. If y equals 3/2 x squared, and if you differentiate this term here and get back to 3x, that means our first term is correct. So let's differentiate it. Differentiating 3/2 x squared means 3/2 stays where it is. We give it a little bit of space. Derivative of this by the ordinary power rule has to come down. We multiply by x to 1 power less, just power 1. So that's how we would typically write it. 2's cancel, and we just get 3x. But it matches that 3x, so that tells us we have the right antiderivative of just the very first term. 2 more to go. Well, we'll also simplify that as we go to the next step, but here's the next term. Plus something. This one's tricky as well, just on its own. We have to think about what happens when we differentiate things and get just a constant. Any volunteers for seeing what should go here? What would be the antiderivative of just a constant b? Yeah, absolutely. So whatever your constant is, multiply it by x, good call, and you have the right antiderivative. So down here, we'll just go 14 times x. And if you're not sure, the good news is we're really good at differentiation, so we immediately check out the second term. If y equals 14x, we can absolutely differentiate that. In fact, we looked at what that derivative would be, even in section 3.2 before differentiation formulas. The derivative of this, which is a linear function, is just its slope, 14. So y prime, even by the power rule, this comes out as just 14. New power on x is 0, so that part cancels out, and it's just a 14. But it matches that term, so that tells us we're on the right track, 2 terms down, and we just move on to the next. Here's the weird one. Here's where we needed section 3.7, all the way down at the very, very bottom of these notes. That formula right there. And that's why I encourage you, whenever a 1 over x comes up and you're just multiplying by a constant, the power of x is not going to change. Leave it in that form because it's easy to see. The antiderivative, it's really that equation. The only difference with that equation, the way we're using it, is you're going this direction, right to left, if you're differentiating. But notice these differentiation formulas, they are double duty. If you're going the other direction, this way, that means you're just finding the antiderivative. So that's telling us, whether we're looking at the formula in the box or just looking at this formula all on its own, from the right-hand side to the left-hand side tells us the antiderivative of that part is the natural logarithm of x. Let's screenshot that in just for the sake of tying together that concept. The formula in reverse is just the antiderivative formula. It still just needs the constant of integration c to make it complete as an antiderivative formula. So on this last portion right here, copying the -5 through the constant multiple rule, multiply this by natural log of the absolute value of x. I'll continue to highlight that in yellow just to convey that's where this really tricky part resolves as natural log x. And then the whole thing is finally complete once we add on the arbitrary constant of integration c. So we know if we differentiate the first two terms, we get the right first two terms on the lowercase f of x function. And if you differentiate this, -5 stays right where it is, constant multiple rule. Derivative of natural log absolute value of x even is 1 over x. That means we have all three terms down, and that's our total antiderivative. All we want to do is clean it up a little bit. The standard way we would write this is f of x is 3/2 x squared plus 14x minus 5 times natural log absolute value of x plus a constant. That was not a big simplification, to be honest. So if you left it in this form, I'm not going to be that super picky. But this would be the standard form that we would typically write it in. Faster to type into WebAssign as well. Well, that's our part A down. Any last questions or comments at all, folks? Getting through that one. Okay, maybe one last comment that's really tricky about derivatives and antiderivatives at the same time. When you write down a function like, say, same one, f of x equals x plus 5 times 3x minus 1 divided by x, one thought you might have is, you know the antiderivative of x, that's 1/2 x squared. So you might put a 1/2 x squared here, a 1/2 x squared here. Antiderivative of a constant is that constant times x. And so you might try to find an antiderivative of each one of these terms separated by the factors and the division. But that method falls flat on its face. If you try to write out that process and then check by differentiating your answer, you'll find you're way, way off from the original function. It's not going to come out as f of x. And it was the same problem with differentiating. If you're trying to differentiate that, but you thought, we know the derivative of x is 1, the derivative of a constant is 0, derivative of that 3x is a 3, and that derivative of that x is a 1, and you say your answer is just 3, then we're also way off. The derivative of that is not 3 at all. The reason it doesn't work is that's a complicated function. It requires a quotient rule, and the antiderivative, reversing a quotient rule, is something that's not even typically done. Not that the formula is impossible, it's just incredibly messy. So whether you're differentiating or finding an antiderivative, things have to be in the right format first. We can't just go component by component. We can only go term by term. Things are separated by pluses and minuses. The moment things are multiplied together or divided together in a weird way, we have to clean it up first. So watch out for that weird problem. We cannot find the antiderivative by forming the antiderivative. It's a long word when you think about it. By forming the antiderivative of x plus 5, 3x minus 1, and x. We really have to take the original function and write it down in this form to get a clean antiderivative to come out. Well, our next goal, let me fix the annotation there. Our next goal is to just practice a couple more to see how these go. Then we'll turn this around to see what's going on in chapter 5. Before long, we'll see how antiderivatives enter into the mix. So here's our next Pretty nasty looking function to handle. But you know, we've differentiated problems almost exactly like this when we were in section, say, 3.3. The way we handled these kind of functions was we did exponent surgery. Square root of x is not convenient to differentiate, nor to find the antiderivative, but we can rewrite it. Square root of x is nothing but x to the power 1/2. So if you can put down the actual exponent, force your base to be up into the numerator, then the power rule in reverse can be used on this piece right here. Let's fix the second one. If you have something even worse, 2 divided by the 5th root of x squared, again, that's something we did handle in chapter 3, section 3. Our goal was fix this radical notation here. The 5th root can take whatever x hat you have to whatever power it is, and we divide by that power. So if it's a 5th root here, this becomes x to power 2/5 here. If it was just ordinary x, it would have been x to power 1/5 instead. Then we really like our base to be in the numerator, or else the way we use both the power rule and the power rule in reverse for antiderivatives goes a little bit different if it's in the denominator. So that's something else we can fix. We keep 2, the constant, multiplied by x to the power of. Flipping up to the numerator just means multiply the exponent by -1. So now it's a -2/5, rather. So that fixes the first 2 terms. The last terms are just ready to go. Any questions at all, folks, with the exponent work here before we throw it back in? Okay, now that we have the proper exponents, we can come back over here and write f of x equals, for the square root, it's being divided by 2, but let's separate out the constant just to focus on the variable part. Let's write it as 1/2 times x to power 1/2. Then it's plus 2 times, seeing our work on the right, x to power -2/5. Then plus e to the x, then -9. So we've got our function in a much, much better form to either differentiate, or what we'll do, find its antiderivative. Here's the process. Just like on the last example, we have 4 terms. We'll just go term by term by term. So focusing on this one, we copy the 1/2 in first, multiply, but put in a little extra space right in the base x. And the very first thing that happens is that exponent goes up by 1. Let's write in a quick note. Up 1 for antiderivative. So that means we're taking 1/2 plus 1. But if the denominator is 2, really all we're doing is just add 2/2. So that's the whole process for that one. Increasing by 1 means adding 2/2. So the new exponent is 3/2. So that's our new fractional exponent from the first term. The moment you have that exponent, you must divide by it. But you know, division is just multiplication by the reciprocal. So the cleanest way to write this is 2/3 multiplied. So just flip it. Or you could write in, take the reciprocal if you like the longer version of that. The reason we're doing this in this form is, you can imagine if you wrote it this way instead, it's a lot harder to look at. It's much more involved looking. This is a complex fraction now, and you still have to simplify it. So we're writing down a lot more stuff, taking more time to simplify. But division by 3/2 is just multiplying by the reciprocal, 2/3, flip it like that, and it's a lot easier to work with, cleaner to simplify. The 2's are just going to cancel out. So that's 1 term down. And we can check these terms one by one as we're producing them. Let's change the strategy a little bit. Let's come up with a total antiderivative and then differentiate the whole thing once we have an answer, just for the sake for folks who would like to see it in that way. So I'll say this one's done with a temporary check. Now we're moving on to this next one where the box is. It's the same kind of idea. It's just a different coefficient. It's 2 instead of a half. Different exponent, but same exact process. We copy down the coefficient 2. We multiply, but we pre-plan and put in a little bit of space before writing down base x. And now if the exponent is negative 2/5, going up 1 means adding 5/5. So here, add 5/5 to that negative 2/5. That produces positive 3/5 altogether. And then once we have the 3/5, we multiply by its reciprocal, 5/3, and that handles term number 2. Actually, those check marks are starting to get kind of messy with all the stuff there. I'll just use highlighting to show we're on the third term now. Well, any questions at all, folks, with the first 2 terms down? Okay, well, the next one's not so bad, right? It fits e to the x. Its antiderivative is absolutely just itself. So that one's done. And if it's just a constant, that's nice as well. For constants, all you do is tack on x. So from -9, we go to -9 times x. And there's an antiderivative. We still have to simplify it, do a little bit more to simplify these fractions, do the cancellations, the multiplications. But if you did all that and left the answer right in this format, out of a 5-point question, we would still lose 1 point. There's 1 point left unaccounted for, and honestly, it's easy to miss sometimes. Anyone see what the last thing is that we must do? Yeah, good call. We require the arbitrary constant c of integration. At the moment, it feels kind of random, but in chapter 5, when we look into some applied problems involving this work, indefinite integrals, we'll see that not putting down plus c really does affect things. That's a required part of coming up with an antiderivative. So it's worth exactly 1 point. If you forgot it in a 5-point problem, no big deal. If it was a whole set where there's 5 antiderivatives and you forgot it on every single antiderivative, you'd lose a point once. And I just mentioned it should be plus c on every one of those questions. Well, we've got that down. We just need to simplify this further, f of x. We do a cancellation. The 1/2 times 2/3 gives us just a 1/3. X power 3/2 plus 10/3 x power 3/5 plus e to the x minus 9x plus our constant of integration c. So there's the full process. We have our entire total antiderivative. Next thing we're going to do is check if it really makes sense, if this is the real antiderivative. Like we mentioned, there's lots of different styles for doing this. Some people like to just check term by term, like we did on the prior problem. Some people do it on the margin, some people just do it mentally, or some people just like to get to the whole answer and differentiate this term by term. So going with that strategy, here's what the check looks like this time. Our answer is above, but now we're differentiating. F prime of x, it's kind of relaxing to do the check. This is just way back in chapter 3. 1/3 stays where it is through the constant multiple rule. The ordinary power rule calls for 3/2 to come down first as a very first step. So here's 3/2, and then we subtract 1, but that just means subtract 2/2. So this is 3/2 minus 2/2, leaving us a 1/2 altogether. And then rinse and repeat. Go plus 10/3, 3/5 comes down. New power of an x, we subtract 1, so that's 3/5 minus 5/5, giving us -2/5 altogether. I'll put a little arrow to show getting that -2/5 on that one. Then derivative of e to the x, no change. The derivative of a linear function just carries in the slope, -9. And the constant goes to 0, so we don't have to write it down. We'll leave it off this time. It's a bit of a mess, so if we took an extra step, we would get 1/2 on the first term, x power 1/2, or square root of x if you prefer. Let's leave it in that form. 3/3 cancels here, 5 goes into 10 twice. So you get 2x to the power -2/5 on that next term, plus e to the x minus 9. Then the moment of truth is, look back up here. We have 1/2 x power 1/2, so these match up. 2x power -2/5, that matches up as well, so far so good. And the rest is the e to the x minus 9. So that actually does equal lowercase f of x. So our work is done on that one. Let's put a small check to say, we did it, folks. That one is complete. Well, that's the process on this one. We're taking a lot of time on these because antiderivatives, they're brand new. So we're being extra careful as we go through these. But once you get a lot of practice, you'll find that coming up with these antiderivatives is not so bad. It is a pretty rapid process. You're using a lot of knowledge you already have on differentiating. And the trick is you're just going up by 1 and dividing instead of multiplying on these power rules. Well, we'll try out another one to round out the notes, but any questions or comments at the moment? Awesome, glad to hear that, Haley. Haley says feeling pretty good with 4.6 so far. And that's awesome. If you feel like this isn't too bad, I'd say that's really good evidence that you're pretty fluent with differentiation. And if you're feeling slightly rusty on differentiation, to really get good in section 4.6, not a bad idea to review your notes. Starting in section 3.3, review the text, get some extra practice in on differentiating, and this becomes a lot more easy to get through. And actually 3.3 is the major section to review because the world of antiderivatives is actually pretty vast. When it comes into, say, things like product rule, quotient rule, and chain rule, those are their own thing. And quotient rule, like I mentioned, is typically not done. Product rule is called integration by parts, but that's way out in the end of chapter 5. The chain rule, we undo that and call it U substitution. That's the second to the last section of chapter 5. So really what we're doing in 4.6 is just working section 3.3, going backwards. That makes it the best section to review. Well, here's our last problem for this section's notes. After this, we're going to turn over to integration. So this gives us a kind of a nice spot to talk about what is integration. After we solve this, we'll put a couple things down on paper to give us a good view of how differentiation and integration all interact together and the role the antiderivative plays. So this one is probably not as tricky as the very last one we got through with all the problems with the exponents. But it is tricky in the sense that now everything is being multiplied except the plus natural log 4. We must expand all of this first. Excuse me. So we must expand. So f of x, to start out, I'll FOIL out the x plus 5 times 3x minus 1. We have -3x times, when we FOIL, we're getting 3x squared minus x plus 15x minus 5. That feels like deja vu. I think we have done that once before already with the quotient version. Then plus natural log 4. Then this becomes -3x times 3x squared plus 14x minus 5 plus the natural logarithm of 4. Then we can distribute the -3x inside to get -9x cubed minus 42x squared plus 15x plus the natural log of 4. So that's its fully expanded form. It's as if someone took this problem down below here. This is the nice antiderivative problem, and they messed it up. Sometimes factoring is good, but it's really, really context sensitive. That factored form is unhelpful for differentiation. You could derive it, but you need a product rule with 3 different factors. But if you expand it, that's the ideal form. This is our simplification if we're differentiating or finding an antiderivative. So in this format, we're just going to use the power rule step by step, term by term. So this time, let's leave the -9 right next to base x. Once we write down base x, exponent goes up this time, so now it's power 4, which means we need to divide by 4. And there it is, just drop it right under that -9. If we're not dealing with fractions, this is an appropriate way to go. It doesn't simplify any further. We typically leave it as the improper fraction. And now let's take the strategy of differentiating this visually as we see each term. If you were to differentiate this 4 would come down right here, would cancel with that 4, and you just get 9x power -3. Tells us the derivative of this one really looks like that very first term. It's exactly equal to it. And so the first term is checked as correct on that antiderivative. So if you like the strategy of just eyeballing it, mentally differentiating what you have to make sure it lines up, it's not so bad. We place a 4 here because when this 4 comes down, it cancels it right off. The new power is 3, matching up with that function. Then we just rinse and repeat. Next term, it's got different values, different coefficient, different exponent, but the process is really exactly the same. We go -42, put the variable x right next to it, increase the power for the antiderivative, so now it's power 3, divide by 3, and that's our new antiderivative. Once again, if we're thinking of what's going to happen here when we differentiate, this 3 comes down right here, cancels with that 3, and it leaves -42x to 1 less power, power 2. So the derivative of that term, that second term, comes out exactly as the thing we want. So that means this term is validated as well. Then 2 more to go. Any questions so far with the very first 2 terms? Okay, and again, another way to think about this is 3 is only in the denominator because differentiation causes that 3 to come down and cancel, and the new power is 2. So you really do get -42x squared. So doing it again, we can do it twice, we can do it 3 different times. Here's 15 power of x. We go 15, throw in the x, but now its power is 1 higher. It's technically power 1, that's just the simplified form. So throw in power 2, which means we divide by 2, but it's been the same exact process from all the prior terms. Differentiating this means this 2 comes down, cancels with that 2, and now it's x power 1. So this validates 3 terms, check as true. But then there's this term. These terms are always tricky. They were a big trick for us when we were in chapter 3, because when you see a term like that one, keep in mind that natural log 4 is a constant. If you differentiated it, it would go to 0. But if you find the antiderivative of any constant, even a weird one, like natural log 4, square root of 3, e to the power of 12 plus 1, no matter how weird that constant looks, in the antiderivative, you write down the constant and hit it with x. Reason that works, let's do a more rigorous check on this one, is if y equals natural log 4 times x, then the derivative of that, it always looks kind of funny when the constant's more built up, but that's just like differentiating 4 times x. Whatever the constant is, it carries down, and x vanishes. So that validates the check on this one. All that's left to do is throw down the constant of integration C. So that's our entire antiderivative right at that stage. One small tragedy though, 42 is divisible by 3. So if we were writing it as simplified as possible, f of x is negative 9/4 x power 4 minus 12 x power 3 plus 15 halves x squared plus natural log 4 times x plus a constant. A lot of writing for just one small simplification there. But we've got it, folks. That's our total antiderivative. Any questions at all getting through that last one? Oh, thank you for spotting that. Yeah, that's absolutely a 14. Good eye. Kind of rough to mess up the arithmetic on that last step. Thanks for spotting that. Other questions at the moment? Okay, well, we've got a little bit less than 9 minutes. Instead of just opening up a brand new chapter 5, my goal for the end of the notes was to once again describe what the antiderivative is really doing for us, describe what integration really is. So here's our next part of the notes that's going to segue us into chapter 5. Essentially, what we're doing here is very similar to what we were describing when we were in, say, section 3.1. We got to describe what we were really doing when we take a derivative, and this was the process. We were finding a limiting value. This will explain how limits were part of the process here of the secant line to get the slope of the tangent line. And that's the thing that we call the derivative of f at x equals a. Integration, same kind of thing. It's a new geometric object, except it's not about slopes of tangent lines any longer. Integration has more to do with areas and antiderivatives. So here's the next graph. This is the one for integration. And my graph is going to look like this. We're going to go from a number A to a number B and draw a function y equals f of x that's above the x-axis, although it could be below the x-axis. I just want a simple diagram to start out. It's a nice continuous function on a closed interval. So the closed interval method applies to this function. Here's y equals f of x. But here's what we actually want to do on a diagram like this. We're looking for an area. An area has a lot of very important physical interpretations, a lot of applications. Areas could be distances. Areas could be energy in physics. It could represent work. It could represent a lot of strange and interesting quantities. The area in this diagram would look like this. There's a vertical line at x equals a vertical line at x equals b, and a horizontal line that represents the x-axis. We'll just draw it on kind of bold. So we have an area that's being bounded by the function y equals f of x, a nice continuous curve, by the vertical line x equals a, the x-axis itself, and the new vertical line. So in integration, we want the area of this region. And in fact, that's exactly how chapter 5 starts out. We're going to start by talking about the area problem. We're going to break it down into terms of a limit, which is going to be kind of interesting way to walk through this. We'll find ways to find these areas by approximating it. But if we take the right limit, we can get the exact area. However, here's what the antiderivative has to say about this problem, and it's really pretty bizarre. This is called the fundamental theorem of calculus. Part 2, specifically. This fundamental theorem was independently discovered by Isaac Newton in Great Britain, as well as Leibniz in Germany. They weren't in communication. They both came upon this information at about the same amount, about the same time. And there's an L in the word fundamental. Let me fix that. The fundamental theorem of calculus ties together differentiation and integration, finding this area, and it does it in the most bizarre way possible. The area of this bounded region that we highlighted here is going to be equal to f at b minus f at a, where f is an antiderivative of the lowercase f function in green. Let's say once again what we mean, just to review, i.e. f prime of x equals f of x for all x in the open interval from a to b. So if we have an antiderivative of whatever this curve is, if we can put it down on paper, we have solved the area problem. And notice how weird that is. All the antiderivative solves is the derivative of f. The antiderivative is the original function f. And we're saying the area of this region, which can be very, very complicated if there's some real curvature to that function, it's nothing but take the antiderivative at the upper boundary, take the antiderivative at the lower boundary, and that's the dead on exact area. This is a pretty wild fact, a pretty amazing achievement of mankind coming up with this particular idea. And this is the sense in which finding area integration and differentiating are said to be inverse processes. Well, that's what we're going to delve into when we're getting into chapter 5. We'll start by specifying the area problem, writing it down in terms of computing areas, taking limits. Then in section 5.3, this is where the fundamental theorem of calculus comes up. And we'll turn back to our whole skill of finding antiderivatives to solving this problem really, really rapidly. Turns out that's all you really have to do to get the area dead on exact. Well, any questions or comments at all, folks, about this wild process of integration and the fundamental theorem? Okay, I think this is good to put down on paper at least once, because when we start chapter 5, it'll feel like we forgot about antiderivatives, but they're going to come back in a major way in sections 5.3, 5.4, 5.5. We'll look into other processes like undoing the chain rule and then undoing the product rule. Turns out undoing the chain rule is easier than the product rule. And it's all going to be trying to get antiderivatives so we can solve this area problem as rapidly as possible. But have a great evening, folks. We'll be back to this when we come back on class on Thursday. Once again, we're at the eve of a third exam, so I'll call for questions before we jump into section 5.1. So don't hesitate to ask if you have any questions whatsoever. But have a great night, folks. I'll see you all next time. Yep, have a good one. Thanks, have a good one. See you later, Haley.